discussed that the racemization of a material, that is also one type of chemical degradation, where our drug is having a specific activity in D form or L form, that is dextro or levo territory. But if we are storing in a particular temperature and conditions, that dextro or levo territory will convert into other form and it will become DL and it will become a racemized mixture. That racemized mixture, it loses its activity because 100% activity will be decreased by whatever which is the racemization happened. Because of that reason, not only these 4 parameters we are going to study, this type of specificity of a drug on a particular rotation of a plane polarized light into the account, and we need to store the product in that particular condition. In the hydrolysis, the system containing the water like emulsion and suspension is fully available. So the drugs which are affected by the moisture from the atmosphere also, they will be having an equal chance to get degraded. So it is usually catalyzed by the hydrogen ion or a hydroxyl ion when compared to neutral. This is the reason most of the times the hydrolysis prone drugs are stored in a buffer which are having a neutral region, maintain the pH at the neutral region. In this active, the drug is decomposed with the solvent, so we are going to remove the solvent water and replace with any another non-aqueous solvent like oil. So that is going to help to improve the stability, because we are not adding the water. So we are going to prepare a oily suspension or oily solution. So that is not containing any water, so hydrolysis will be avoided. Usually solvent water is sometime reaction may involve the pharmaceutical co-solvents. We need to add as a preservatives or certain things we are going to add as solubilizing agents or wetting agents. These also enhance the hydrolysis. Sometimes if their content is more, they will also going to get a protection. Most of the we need to see that non-aqueous solvent, if they are humectants, the humectant materials are prone to get absorbed the moisture from the atmosphere. So availability of the moisture will be more, and we are going to face the problem of hydrolysis with the humectant solvents, even though we are avoiding the water. Many cases, drugs undergo the hydrolysis are the esters and the amine and alkali acid. These are all more prone to. Most of the times in the presence of alkaline acid, these esters like esters and amides, they are going to get cleaved. This is what we have already seen, the acyl linkage, that is acyl acid cleavage. In that RCOR, say it is an R1 in the case of ester, and R is your carboxylic acid. When reacting with the water is ionized to OH minus and H plus. So you are going to get release RCOH acid and HOR, that is R1. If you are designating as a different moiety, it is R1. If it is the same moiety, like it is maybe any ethyl or propyl group or such things, you are going to have a same R. But in that case, it will be cleaved into alcohol. This is more permanent reaction, and it is going to undergo very fast when compared to esters and amides. Amides are having a more stability with respect to hydrolysis. In that cases, if you want to prepare a salts to make the drug more you are going to, so it is susceptible to the specific acid-base hydrolysis when compared to a general hydrolysis. In a specific acid-base hydrolysis, a specific moiety of acid which is prone to get more. So in those cases, we avoid such a case of excipients without you adding in them. It involves the amine linkage cleaved. Give the amine instead of alcohol of the esters, what we are going to get. For example, you have got R. In this case, if R is different, then we are going to call it as R1. it is an amide reacting with H2O. So it is above or below, we are going to add either acid or a base as an catalyst, and it enhances the fastness of your reaction. These reactions which we are going to use for the practical also in nearby future, most probably next week we are going to do. We are going to study the ester hydrolysis. In the ester hydrolysis, what we are going to do in the practical, we are going to take RCOR. In that R is one R is acetate, another one is ethyl group. Ethyl acetate we are going to take. That means acetic acid reacting with ethyl alcohol, getting ethyl acetate. After cleaving, it will produce acetic acid and ethanol. So this is actually what the reaction which is going to progress in the lab, and we are going to add intentionally water to hydrolysis and rate of reaction. First thing what we do is whether the reaction what it is following in this particular case is zero order, or it may be a first order or second order. That is one. The second thing is which we are going to do is we add something in excess, because more the order, more the complexity in the calculation in the practical. So we add one component in excess. When you are adding an excess, say for example, if you are reacting in the presence of alkali or acid, so then what will happen? We are going to have an hydrolysis. If we are adding one component in the excess, so you are going to have a pseudo orders. So we are going to study that also. So we are going to have 3 practicals based on this particular reaction, what you are observing now. So these 3 practical, there we are having a ester hydrolysis only to give an example in the practical how we are going to get a study of which order it is following, what is its rate constant, how to calculate the shelf life, so that I am going to preserve that without any degradation. All these things which will be easily calculated by taking a simple moiety, considering as a drug. And in actual, whenever you are working in a company, our drug is maybe present like a chloramphenicol or barbiturates in the case of amides, and aspirin and atropine and physostigmine or procaine like ester drugs. We are going to handle them and see the precursors or the cleavaging product we need to study to see the progress of reaction by keeping under the water, that is aqueous conditions, and we need to withdraw the samples and study. This is what we are observing generally, and we make an attempt to see the what is its kinetics and half-life and shelf life and the prediction of the expiry date. Similarly, we are having one experiment in our practical to study the effect of temperature to see that particular stability analysis. Increase the temperature for the same reactions. We are having one practical reaction of at room temperature 25, and you rise the temperature. When temperature is increased, what is the effect on rate of reaction we see, and we will keep on making a graph. So it is, if it is a straight line, we will extrapolate to 25 degrees. We conduct at higher temperatures and make it very fast reaction within 30 minutes, like that it will happen. Otherwise it will take 1 day, and we will extrapolate to the normal condition of 25 without doing at 25, because if you take, you need to stay for 25 hours, 24 hours or 48 hours, then your practical will not be completed. So you will add component of temperature there and enhance the rate of reaction. Within 5 minutes to 10 minutes it will progress the reaction very faster by heating at 50, 60, 70 like that. And if it is straight line, extrapolated to the room temperature, and you find out what is its rate of reaction. And after knowing a rate of reaction, you can calculate the shelf life and half life by knowing the rate constant and equations. So this is the strategy which are going to help us by seeing its stoichiometric equation and the pathway and environment of the catalysis, and we are going to remove them in actual practice in formulation manufacture. Generally, we are going to see that in the how to protect from the hydrolysis, enhancement of the stability with the hydrolysis. Most of the time, some drugs are present which are generally we are using for the hydrolytic degradation, or esters like aspirin alkaloids we have already seen, And lactones, pilocarpine and spironolactone, it is a diuretic. So amides like a chloramphenicol, imide like a glutathamide, and malonic ureas like barbiturates, all like getting acting with respect to the hydrolysis and getting affected. Now we are going to see how to protect against the hydrolysis if you are making it, because we are studying the shelf life. You feel that my shelf life is very less. I cannot launch the product. Then what you can do, you cannot change your drug, because the drug is already fixed to treat the disease. You want to launch your product with it by any means. Otherwise, your competitor will launch some by applying the knowledge and doing the research. So how to enhance its stability? And we are going to see by the application the different approaches. First, we need to learn what are the different approaches available in the protection against hydrolysis, and we need to avoid. So avoiding the contact with the moisture at the time of manufacture is ideally required. There, I have already mentioned, we have learnt in the measurement of humidity in the pharmaceutical engineering, and we are going to have that. And packaging in the suitable moisture resist container and the strip packing. If anybody say that is it already completed, or am I repeating in now? Is it already completed? Completed?
No, sir. Protection is not completed. Only hydrolysis types was completed, sir.
Okay. Because I am getting section D, I got some memory. It is appearing that I thought it, because both the sections are present. Good. This is very important question with respect to GPAT and your sessional. The 5 marks question you will be asked is how to protect the drugs from the against the hydrolysis. There are sometimes you will be asked explain the hydrolysis type of degradation, the principle of hydrolysis for the degradation of the product, and the protection against that. Both the together you may be asked a question in a 10 marks. In both the cases you need to explain, and these are all the things which are giving different strategies to protect your hydrolysis. First thing is avoid the contact with the water and the moisture which is present in the air in the form of water vapor by reducing its relative humidity. By reducing its relative humidity means first we need to measure the humidity of the room. If it is very higher, say for example we are taking sometimes 75% we have got in our lab. In such conditions you are preparing a product, manufacturing a product. So during the manufacturing itself the product will degrade. Then what you do? You need to reduce the humidity. How you need to reduce the humidity? Dehumidification we have already studied in previous year, by compressing it, by cooling it, or by using a water adsorbents and passing the air through them and releasing into the room. By doing that, the humidity will be reduced to the 20 like that. Then your moisture will be having less contact with the product during the manufacture, so you will be protecting your drug. This is one strategy. Preferably, we need to employ it and inform to production people to use specific RH. Don't increase that because the product will degrade. Most of the times, the second approach is the packaging. So while doing manufacture, we do it, but during the packaging, it is getting exposed to the environment. It will absorb the moisture from the environment. So we need to take care by the moisture resistant pack. What is the moisture resistant? Like a strip packing, because in the aluminum foil both are there. It is pressed, cold pressed or the thermal press. When they are getting there, they will be completely adhered. They will not allow any moisture to enter into the pack. The strip packing is completely moisture resistant pack. So when some person is required to take the tablet, he will pierce and cut the strip and take the tablet or capsule out, and he will take it with a glass full of water. So the storage controlled by the humidity and the temperature is one for the safe side, but the packaging itself, it is completely closed, it will protect it. So we will be avoiding that particular type of degradation. But you can do it for the tablets and capsule. You may get the question, sir, I want to dispense my product in form of a syrup or a liquid dosage form like a suspension and emulsion, where I cannot avoid it. So I'm bound to add water or a solvent. In that case, how can I put in a strip? Strip is not possible there, because the strip is the one which is having a slots like a 10 tablets you are putting in one strip. So you cannot dispense it. In that cases, hydrolysis, most of the times acid or base is catalyzing it. We need to maintain an optimum pH in the neutral range by you adding a buffer. We need to select a suitable buffer, and we are going to select the buffering agent components in such a way that they don't have any incompatibility problem with your drug, and we need to select them. Sometimes what will happen, different buffers are available to maintain the pH in the neutral region, but you can have the acetate buffer and phosphate buffer for the topical preparation. You have got borate buffer. Sometimes what will happen, your one type of buffer may not be suitable. Phosphate buffer may cause the further degradation and stability problem. You need to use another buffer. So in that particular case, you need to select a component of the buffers that is very much critical, not only the pH where you are and making it, because the components are incompatible to with your drug. Even though they are excipients, we need to select them with due care. So we are using a concept of buffering agent to maintain the pH in the neutral region or a particular point where we are going to have this hydrolysis under the lower rate. It means the rate of degradation is lower by maintaining the pH at that particular condition. How will you know? You need to see, similar to the effect of temperature onto your degradation, you are going to study the effect of pH onto your degradation. So you will be maintaining at a different pH like 5, 6, 7, 8, 9, 10. And under these conditions of the pH, how the drug degradation is present, you study it and you plot a curve. And the where you have got V-shaped, the apex of the V which is facing the bottom, that pH is corresponding pH you will select for your maintenance of the pH that is using of the buffer. Hydrolysis of certain drugs like benzocaine and procaine, they can be decreased by the addition of a specific complexing agent. So most of the times, some another component which are inert or it may be a drug also, they will be mixed with that, they form a complex. By forming a complex, the amide or the ester linkage will be more getting protected or shielded by adding this complexing agent. This is excellent approach where you need not add any buffer also, no problem, but the complexing agent, it will protect the hydrolysis and it will enhance the stability and shelf life. This is one approach, is an excellent, but it is not possible for all drugs. We need to have a complexing agent mechanism to prevent its degradation. Most of the times, this is done by the formulation scientists, not the drug discovery people. During the drug discovery, they find that what are the suitable salts which are present, like I need to prepare a benzocaine hydrochloride or benzocaine phosphate or any amine salt in any manner I need to make it. If it is present in a stability of a particular salt, they will release the product in that particular salt form. But we need to see as a formulation manufacturer doing a research by adding a simultaneous complexing agent, another drug and an excipient that will enhances the stability, we need to add it. Another way of protecting the hydrolysis is susceptible because in the case of penicillin, it is also containing the ester linkage and its derivatives like amoxicillin or anything which are antibiotics which we are generally using, that can be prevented by the formulating them in a dry form. It is like we are dispensing as a dry granules and putting in a bottle, and we will be put mark in a bottle and ask the patient to reconstitute by adding a pre-boiled and cooled water. So this reconstitution, it will convert the dry powder into a suspension by shaking the bottle. It means you are preparing the suspension in the home, not in the factory, and asking the patient to prepare the suspension at his home and it is own hands. But he will not have any purified water in the home, and he will not have a water for injection like that. And if you supply along with the water for injection, it will become a costly. The product will become a costly. So what you do, you write a packaging insert. You just boil your water so that you kill the germs, and close the vessel with the lid so that no exterior microorganisms will enter, and cool it. After cooling it, you add that water for the reconstitution so that it will be equivalent to a sterile water and cheaper also. It can be possible in the home. Because of that reason, this dry powder for the reconstitution is the best methodology which is used generally for the penicillin and other derivatives, amoxicillin. which are required to be given to the old age patients and children. They cannot consume tablets and capsules. Sometimes what is the best option is you prepare the penicillin and amoxicillin as a tablet, because here the problem is you are asking the patient to have boiling the water and cooling it and making it with the error. He may be adding more water, or he feel with a parallax error he will be adding less water. You should not give the job of pharmacist to them, to the patient. So these errors will be occurring in the illiterate persons, and they are not having little bit knowledge about this reconstitution and how to make it. If an error is occurred, the entire bottle will getting spoiled. In those cases, what we can suggest is you dispense the tablet in penicillin as in form of a tablet. The tablet is not like a regular tablet. What is a regular tablet? If you are taking a regular tablet with the 250 ml of the water, it will take longer time and it will be making it not immediate effect. We want to have a immediate effect. Another thing is we want to give in the form of a suspension. So that is the reason we are giving in the dry form and asking them to reconstitute. So we cannot dispense directly like a regular tablet. What you can do is dispersible tablet. Dispersible tablets are the tablets only. You don't take like a regular tablet. In this case, what you do, you take a half glass full of water and add a tablet in that, you shake it. The tablet will become broken and it will become a suspension while shaking. And you drink that suspension. In this particular case, your regular tablet, what you are taking with a glass full of water, you are splitting a glass full of water into two parts. Half glass full of water you take it, add a tablet in that, shake the glass, and you drink it. Remaining off you drink later, and it will become a same one, and it is reducing the errors in the foam to take a dry powder and reconstitute them and taking a dose also. In this particular case, what is the extent is you are giving entire form of a dose which is already measured and placed in the tablet. So the person will not take less or more. In the case of suspension, what will happen? He can, if he feel that flavor or the color is pretty good to the patient, he will take more. If it is bitter or something he does not like, intentionally he will add a less and he won't take. In this particular case, what will happen? You are adding as a tablet. So the tablet, you will not take a piece and take it out. I don't like it like that. It will not be happening. Another thing is we are giving in the tablet form, and we are adding to the regular water only, and you are taking clean water along with glass full of water. You are taking just like your cool drink, what you are taking it. It will appear like similar manner, and we can dispense it. These are all the approaches at the manufacturing level of a drug, at the invention level and the formulation level, and during the manufacturing, during its packaging, we are going to take. You see, we are attacking at the manufacture, that is by reducing the moisture. We are attacking at the packaging by reducing contact with the environment. We are suggesting liquid only by adding a buffer. And we are also reducing it by giving in form of a solid, like a tablets and by adding a complexing agent. And we are also adding by reducing it degradation by dispensing in form of a solid only, but it requires to be reconstituted. These are all the approaches which will protect against the hydrolysis and increases the shelf life. Otherwise, your shelf life of a tablet is 1 month. By doing these approaches, it will increase to 3 years to 5 years. This is actually what the advantage. Another approach is oxidation. Where you are having a better major degradation by the chemical means of degradation. Oxidation we are already learning in our chemistry, and we know it, the impact. So oxidation is controlled by the environment. Most of the times it is light and trace element and oxygen presence, that is O2 is present in the air, and oxidizing agent. It means there are the four major things which are affecting the oxidation. One is light. Light by itself it will not cause oxidation, but presence of the light enhances the oxidation reaction, because it will produce the photons supplying to reaction, that energy enhances the rate of reaction of oxidation. Another one is the trace elements like your heavy metals that will also enhance the oxidation degradation by creating the free radicals. These trace elements, what they do, they create a nascent electrons and the free radicals. That free radical, it will initiate the chain reaction, and chain reaction will be progressing it. Oxidation mechanism. This is the one another problem. Another one is the molecular oxygen which is present in the air in the form of O2. We breathe in and breathe out during that environment. So it is also getting exposed to your product, and you are going to have a degradation. Another one is oxidizing agent which is present in our product as excipient, and drug itself may be oxidizing agent. So this is actually what the oxidation more factors which are there. There are 4 major ones. So it occurs when exposure to the atmospheric oxygen, it is present. Most of the times it is a major phenomena and a problem we are going to face. And either the addition of oxygen or removal of the hydrogen, we call it as an oxidation in the mechanism. It is also called as addition of removal of the electron, or it is also called as addition of removal of hydrogen or electron, which we are calling it an addition of oxygen as the oxidation. So the electron mechanism also redox potentials, we need to discharge of a moiety onto the oxidation at the molecular level. It is having an impact. Oxidation is the loss of electrons, that is the removal of electrons, while reduction is the gain of electrons. So this approach is also we see into the account. We need to see in those cases ion to take a consideration in the progress of oxidation reactions. Auto oxidation is another major phenomenon we are going to have in our product. It is triggered by itself without intervention of O2 that is present in the oxygen in the atmosphere. Oxidation, what we have seen is presence of the oxygen in the air, and it is making it, progressing it. In the auto oxidation, which is enhanced by itself without triggering point by the O2. How it is happening? This reaction between the compounds and the molecular oxygen is required to be initiating the chain reaction called as auto oxidation. This initiation is required by auto. It is present in because oxygen is already present, dissolved in the formulation in the water. Oxidation, auto oxidation. In the auto oxidation, what will happen? Free radicals are produced during the initial reaction. It is the first only. Later onwards, it will not be present there. So in the first case, it is getting the free radicals, and they are highly reactive, and further catalyze the reaction of additional free radicals are getting produced, and this chain reaction will keep on going, and your drug is completely getting degraded, and it will end. So drug in your body. Most of the times, what will happen? Heavy metals like copper, iron, cobalt, nickel, these metal ions, they will be having a catalyzing the oxidation degradation. So they create this radical chain reaction, and it is catalyzing. And the heat and the temperature, obviously they will also, that is the temperature and your light, it is also influencing and enhances the kinetics most of the time, because both are energies, heat energy and light energy. They supply the energy of activation, that is called as EA. We are going to study in the stability analysis. So this activation energy is the minimum energy which is required to progress the reaction. If our formulation or the drug which is having a critical energy lesser than that activation energy, it won't degrade. But when the activation energy is enhanced above EA for that particular reaction progress, this is supplied by the heat and the light which is present in the environment. The progress of reaction will be enhanced. Because of that reason, we are going to protect it from the heat by putting in the cool place in the refrigerator, and protecting from the light in the amber colored bottle, and we are going to protect these metal ions by adding a complexing agent to them. So we can protect this oxidation. It means if you know how the oxidation is happening in the principal part of your 5 parts and explore the mechanism of oxidation degradation, you know the prevention also. That another angle we are going to other side of the another side of the coin, it is having a prevention, because the problem itself it is having a prevention approaches. We need to find out what is the problem there, whether it is the presence of vapor, it is the presence of heat or light, or it may be the presence of environmental oxygen that is O2 in the atmosphere, or it is progressing by the electron lossy, that is loss of electrons. How it is progressing, accordingly we need to take a prevention methods to prevent the oxidation degradation process. So now we are entering into the seeing the protection against the oxidation, because this is second way of 5 marks question you are going to have. What is the mechanism of oxidation process degradation, and how to protect from the against the degradation of the by the oxidation. So the first thing which we are going to use generally to protect the oxidation, usage of the oxidizing agent. One approach is you add oxidizing antioxidants. This they are highly oxidized. These antioxidants will be working by the different approaches. We will see. There are 3 major approaches. The antioxidants are present in the GPAT. You will be asked this one mechanism of antioxidant actions. So they will be giving some moiety how that is getting producing antioxidant property. So there are 3 types present. The first group of antioxidants, they prevent the oxidation and they will enhance the stability of the product by inhibiting the oxidation by reacting with the free radicals. It means they don't allow the free radical to degrade the drug. They act on the free radical and they will be reducing the free radical chain reaction. Example is tocopherol, butylated hydroxyanisole, and butylated hydroxytoluene. These components you might have already used in the first sem of your B Pharmacy course during your formulation manufacture. We are calling it as a PhD. They are required to be added very little concentration because they are these free radical scavengers. Most of the times they require to be 2.01%. Is the one which you are generally adding a component. It is sufficient to produce by scavenging the free radicals, scavenging them, and they will be reducing the free radical chain reaction, and also oxidation will not be present, and your product will be protected. This is one way we are going to have this antioxidant activity. And the second group of comprising is the reducing agent. They themselves are reducing agent, have a lower redox potential than the drug and other substance. They should protect, are therefore more readily to get oxidized. It means they sacrifice themselves in the place of drug and protect the drug. It means we are adding another component. That component is not important to us, and the oxidative component of that one is not toxic to us, like your ascorbic acid, vitamin C. We are adding that component in our product, or isoascorbic acid and ascorbic acid. This will, what will happen? They will be having high oxidation, prone to getting oxidized when compared to your drug, because whatever the oxygen which are available, they will getting oxidized, and drug will be later will be involving it because it is more prone to get oxidized. So first they will be getting oxidized, ascorbic acid getting oxidized. Then what will happen? Your drug is protected. Similarly, potassium and sodium salts of metabisulfate, sodium metabisulfite and potassium metabisulfate. These are all the GPAT questions. How potassium metabisulfate is working as an antioxidant. It is acting as an antioxidant in the sacrifice method. It is sacrifices itself to protect the drug. In advance the drug, it will degrade first, so it will protect it. That is the reason we are adding. So this is actually the degradation product of what it is being there is not harmful to us. So drug is getting protected. This is second approach. If degradation product of why we are taking only ascorbic acid itself, it is good to our body to increase the resistance, and its degradation product is also not harmful. Sodium metabisulfite and sodium bisulfate, they are not harmful to our body because they will be present as a sulfate ions in our blood. Phosphate, sulfate, acetates, these are all the present within our blood, so no problem. So we are going to take them. There is no harm, and if they are present, if they are not consumed, also no harm. Even they are degraded by the oxidation process, also no harm. But drug is getting safe. This is one approach. The third approach is little antioxidant effect by themselves, but they don't have antioxidant by themselves. If you add alone, they don't have, but little. But they are enhancing the action of antioxidant, like citric acid, tartaric acid, sodium, disodium, meditate, and lecithin. These are all. What are these? They are all complexing agents, chelating agents. This chelation or the chelation or complexing agent. So this is the use of chelating agent. When heavy metals, they catalyze the reaction of a free radical. So we are adding this component of a third group, EDTA. How it is having an antioxidant action? Mechanism of antioxidant action. 5 marks question you will be getting. Right, the different mechanism of the antioxidant action to protect your degradation by the oxidation in the pharmaceutical formulation. So this is the third group, is a complexing agent and chelating agent. They are having a scavenging of the heavy metals, metallic ions, EDTA, citric acid, tartaric acid, and form the complex. The complexes, they will not allow the metal ions to react and make a progressing of an oxidation. So that is the reason they are preventing it. But they alone, they can't do it. But the presence of metallic ion, they increase it and catalyzing the reaction. By removing them, you are having the protection. This is actually major advantage of this we are going to have. Now, we are proceeding with photolysis. That is the effect of the light on the degradation. Photolysis is the effect of the light. It means exposure to the light causes substantial degradation of the drug moiety. We have already seen that any drug reaction, it requires the activation energy EA. That critical activation energy will be supplied by the environment to get a progression of reaction. If the moiety or a formulation which is exposed to the EA lesser than what is required to have a reaction, it will be stable for longer period of the time. But when the activation it is enhanced by exposing to the light, it causes the photon. The photons are entering into the bottle and it will enhance the reaction that causes the damage. For that purpose, the molecules are exposed to the electromagnetic radiation. They absorb the photons. At the characteristic wavelength, they are having a high absorbing tendency, which causes the increasing in the energy, which can cause the decomposition. And they will be getting transferred to one form to another form. And they will be more prone to get converted by the heat further because the activation energy further may. And the result in the light emission at a new wavelength. So it will also further degrade by having a generating the fluorescence and phosphorescence. Most of the times we have got anti-malarial drug like quinine. It is having a fluorescent mechanism. If you eradicate and apply the light on it, if you remove the light also, it will produce. It will produce. Or it is producing high energy radiation emitting it. It means we are allowing the product to degrade by having these mechanisms. In those cases, we prevent the exposure to the light. That is the best one. Generally, we can't do it because the bottle or a manufacturer, anything which is required to be present, or it is required to be manufactured and exposed to the natural sunlight. The natural sunlight generally it lies in the wavelength of 290 to 780 nanometers, which is present in the sun. And we have already seen in the initial sections like the lower the wavelength and higher the energy of activation and its damaging effect. So high energy is present in that for the particular proton. So the natural sunlight which is in the wavelength of range of 290 to 790 of which only with the higher energy. Higher energy means lower wavelength. What is the lower wavelength? 290 to 390. That is more prone to get a degradation of the drug. So this region, when you want to protect the drug, it can be done by the preventing and filter the visible radiation not to enter into the bottle. How to use the filtration? The filtration of the light can be done by the amber color bottle. This amber color bottle filter this radiation which is in the range of 290 to 320. This is GPAT question, and you are going to reduce its exposure. It won't prevent the entry of above 400 to 780. Amber color bottle will not allow the, because we are having a protection of the light means we think that it will not yellow even when it's 400. That is VIBGR region. What we have seen halogen effect recently. In that case, we have seen the VIBGR that is in the range of 400 to 780 nanometers. So that is the reason we are able to see with the naked eye. Less than 400 we cannot observe. We need to use a microscope. So that is, we need to use UV spectrophotometers. Otherwise, the visible eye will not be able to sense it. In this particular case, the damage is less, and even if you don't prevent also, there will not be any problem. But the amber colored bottle, they will not prevent the entry of these VIBGR wavelengths. They will enter into the bottle, but their impact onto the dosage form is very less because there is visible light, wavelength is higher, and energy is less. So the lower wavelength region and higher the energy and cause the more photo degradation effect of the drug. So example of the phototoxic drugs are the furosemide, acetazolamide, and cyanocobalamin, so which are having. And some another example is very example, and GPAT question is there, sodium nitroprusside in aqueous solution, which are administered by the IV infusion in the management of hypertension, which is a critical case. If you see the shelf life of it, if it is protected from the light, it is stable for at least 1 year. But if you expose it to the light, it will be stable only for 4 hours. So just imagine how much difference it has got. The impact of the light, it is enhancing the rate of degradation. Just without protecting, and in the normal room light, it is having only 4 hours of stability. So if it is protected from the light, it has enhanced to 1 year. That is the reason we suggest to the patient the storage condition, so that we will be having how the effect of storage, which is having an impact. So you need to store like that only. So how to enhance the photolytic degradation protection? How we want to make it? We've already seen during our journey of how it is causing a mechanism of action, and there itself there is a solution. One is use of amber colored bottle. Amber colored bottle prevent the and filter the high energy wavelength not to enter into the bottle. That is in the UV region. The UV region will not be yellowed. Only visible region only it will yellow. This is one thing. And storing the product in a dark, that is in a cupboard where light is not present, and packaging in the cartoons where you have got a paper and plying is present. What is the ply? 2 ply, 3 ply, which is having a cushioning effect and more dark atmosphere it will produce. Generally, we are putting a bottle in the packaging cartoons, and we have sorry, they act as a physical barrier to the light and prevent it. Another one is we are going to have sometimes the aluminum foils also, which is required to be used in our lab generally, because whenever you have got a practical, you need to protect your round bottom flask, you need to protect conical flask. You are doing your analysis and you are employing approaches to prevent the degradation of the product by the light. But you are going to do in the light only. In the dark, you cannot see your burette or